So what I want to look at today is the law of cosines, and I actually want to derive this. Okay, so you don't need to copy this down or anything like this, because I just want you to see what's going on here. Okay, and by the way, this is one way that people can come up with these kinds of laws or formulas that we use all the time nowadays. Okay, this is what's known as a coordinate proof. All right, you may have done some of this back in geometry, maybe not this complex, but some types of coordinate proofs. But basically, we're on an XY plane here, and I've drawn a triangle where point C is at the origin, and I wanted this side of the triangle BC, to be A units long. So I put it on the x-axis, so I could just call that point A0. All right? So I've got this side here, A units long. It's the point A0 right here. Okay? But then we have this point up here to make triangle ABC. I called this point B cosine C and B sine C. All right? Now, you might recognize that a little bit from the unit circle. In the unit circle, the radius was 1, so all the points on the unit circle were cosine sine, right? Well, here, C is the angle that we're working with here. C is this angle. Okay, it's the angle of the triangle. And if you look at this little right triangle here on the left-hand side, okay, we could use right triangle trig to find how long this bottom leg would be, which would be our x coordinate, and how long this height would be, which would be our y coordinate. Okay? So I'm going to use right triangle trig here, and I'm saying that the cosine of angle C is the x coordinate over side B, because B is the hypotenuse of this little right triangle here. Okay? So, of course, now I multiply both sides by b, and I get x equal to b times the cosine of angle C. And that's where we get this x coordinate from. Okay? I do something similar for the y coordinate. Instead of cosine, I'm using sine of angle C because it's opposite over hypotenuse. So it's y over b. Again, I multiply by b, and this time y is b times the sine of angle C, and that's where I got this y coordinate. Okay? So you'll notice I'm looking at this triangle ABC that's not a right triangle, and I'm working with it by dividing it into right triangles. Okay? So now I'm going to focus in on the triangle on the right here. Okay? My goal here is to find the length of side C. You might say, well, you don't know the measure of anything. I know, but we want to get an expression for the length of side C using A, B, and angle C. Okay? Now, since I have this right triangle, if I can figure out the length of this vertical leg here, and I can figure out the length of this horizontal leg, then I can use the Pythagorean theorem to figure out what angle C is. Okay? Well, the nice thing is we already figured out that y is b sine of C. I'm going to redraw this triangle down here. So I have b times the sine of angle C. All right, so I just redrew the right triangle down here. Okay, this is side C that we're looking for. But what about this bottom leg here? We know the whole length of this is A units long.
1/2 n.
Maybe, but we don't know it's exactly half.
So A minus
b cosine C?
Well, what is b cosine of C?
So the full thing would be 2.
Well, it kind of looks like half of it, but again, we don't know it's exactly half.
So you could say A minus 1/2 CV.
No?
Again,
but you're on the right track. A minus,
B cosine C.
yes, there we go, okay? So here, if this is B cosine C, then this is going to be A minus B cosine C. Does that make sense? Okay? So A minus B cosine of angle C. That's the length of this side here. Okay? Now, I've already written it on the bottom here, but you can now see how we would use the Pythagorean theorem with this right triangle to do leg squared plus leg squared equals the hypotenuse squared. Okay? Whoop. I don't want to undo, I want to redo. There we go. Okay? So, we have A minus B cosine C squared plus B sine of C squared equals C squared. Okay? So let's actually work on some of the algebra here. Okay? In order to square A minus B cosine of C, what do I have to do?
A squared minus 2ab cosine c plus b cosine c squared.
A squared minus 2ab cosine C
Plus b squared cosine squared c.
Okay? Yes, we are foiling. Okay? Do be careful, we would have to foil that. Alright, but that's what we get. Okay? And then this squared would equal what?
b squared sine squared c.
B squared sine squared C. Very good. Okay? And that all equals C squared.
Sine squared 1
Okay.
minus.
We can go that route, but actually we'll do it even a little bit faster. But does everyone get what we've done here so far?
No.
If I do it out, then yeah.
Oh no, I see.
Yeah, write this twice and foil it if you need to see that. That's fine, okay?
The two last terms is equal 1.
Okay.
Oh, okay.
Alright, now, Davi's pointed out these last two terms. By themselves, they don't equal 1, but there is something to what he's saying here.
b squared 1.
B squared is 1.
There we go. Okay, look, they've got a b squared in common. Alright, so I can factor out a b squared, and look, we've got a cosine squared c plus a sine squared c. See, these identities don't go away. They're really useful all the time, in a lot of different cases. Okay? Because cosine squared c plus sine squared c,
Equals 1 squared.
that equals 1. Yep, that's 1. So I'm going to rearrange a little bit just to make it look a little prettier here, but we got c squared equals a squared plus b squared minus 2ab cosine of angle C. And we just derived and proved the law of cosines. Okay? Alright?
I knew we could do it.
So we just derived the law of cosines, and that's what we see right here. Okay? A little bigger and clearer here for you. Okay, c squared equals a squared plus b squared minus 2ab cosine of angle C. So you notice here it's got the Pythagorean theorem in it. C squared equals a squared plus b squared, but then we have this minus 2ab cosine of angle C.
Kind of a Pythagorean theorem triangle.
Okay? Yeah, so this will work.
Oh no, but monsieur, this is the small letters or sides, right?
The small letters are sides, the big letters, remember, are angles. So that angle C is right here. And this is something I wanted you to point out here, okay? This side right here has to be the side across from the angle that you know, or you're trying to find, depending on what you're given. Okay? So these have to be across from each other. These are just the other two sides of the triangle. Okay? Now, if you look at your book or other books or websites or whatever, you'll also see two other variations of this formula. You'll see this. A squared equals B squared plus C squared minus 2BC cosine of angle A. And you'll see B squared equals A squared plus C squared minus 2AC cosine of angle
B.
B. Alright? Do we need to memorize three different formulas?
No.
No. There's
One.
nothing special about which side is named A or B or C.
Just the cosine has the same letter with big.
Okay, yes, the cosine, the angle that you're using has to be the one across from the side that's by itself. It's easy to remember. They're across from each other in the equation, so they got to be and they've got to be across from each other in the triangle. All right, so don't take the time to memorize three totally different formulas. Memorize the one and understand it, and you'll be all set. Okay? We'll see that here in just a second when we do our first example. Okay? So when do we use this formula? The law of sines we used whenever we had an angle and a side across from each other. Okay? This we're going to use if we know two sides and the angle between them. Okay, remember side angle worked for law of sines, but side angle side did not. Well, here side angle side will work with the law of cosines. You can use that to figure out your third side, or if you know all three sides, you can figure out one of the angles. Okay, your variable would be the angle, and you would just solve the trig equation. Okay?
Is side angle side different from side angle?
Yes.
Yeah.
The angle has to be the one where the two sides you know meet.
Okay.
It's between them. Yeah. Davi?
Does this work in all the situations where the love sign works too?
No. That's the thing. I should say this. It can, but it gets more complicated. Because, here's the thing. If you fill it in and, A is the variable, so you've got an A squared plus a number minus 2A, and you've got variables here, yeah, you've got a quadratic equation, and you could solve that. But if you see yourself doing that, then you probably could have used the law of sines instead. Alright, and that's a simpler formula, so I'd rather use the simpler formula. Okay?
Can you explain side angle side and side thing?
Yes, let's actually do an example of both of those, and you'll see what it looks like. Okay? Here's a case where it's side angle side. Notice we know side AB, or side C, the length of C is 15. We know the length of side B is 21. And the angle where those two sides meet, the angle between them, is 10 degrees. Okay? So we have side, angle, side. Okay?
So that's based on just what you're given.
Yeah, it's based on what you're given.
Okay.
And as a result, we're now able to figure out the length of side A. Okay? Now, this was the formula we looked at, but remember we said that the letters that are used are pretty arbitrary. The key here is that we know the 10 degree angle, so we're going to use the cosine of 10 degrees, and that means what has to go over here by itself?
The little a squared.
Yeah, the little a, okay, because the angle is across from the side that we're trying to find here, okay? The rest of this we can fill in with the 15 and 21, and it doesn't matter which one we use in which place. We got 15 squared plus 21 squared minus 2 times 15 times 21 times the cosine of 10 degrees. Okay?
That's confusing though, because it's C squared and B squared, not A squared and B squared.
Yeah, well, and that's where I said, other books will give you 3 different versions of the same thing. They just rearrange the letters. If you understand it, though, the angle and the side across from it, the other two sides go there and there. Okay. And at this point, really, it's just a matter of plugging it into your calculator. Okay? So we get a squared equals 45.57. Okay? And then you square root that and you get a equal to, what is it?
75.
6.75. Okay? And we don't have units here, but we can just leave it at that. Okay? Yes?
I find negative 39 with that. I did like those 225 plus 441, which is 660, and minus 630 is 36, and 36 cosine 10, I got negative.
Well, hang on. Follow your order of operations. You've got to do all this multiplication and then subtract that whole product.
Got it.
Yeah, be careful with order of operations on this.
Choose the number to take off and then put in the unit.
The units on a word problem, you're going to lose a half a point if you don't give me units. Okay.
Fraction?
Yeah. Okay.
What?
Not half the question, half of a point.
Oh,
All right. So like if you're given a word problem or something, it's supposed to be like in miles or something like that. You need to give me miles.
what if the problem is half, counts half? Like, the whole problem.
I'm not gonna give you a whole problem that counts for half a point. So. All right. Now, just as like a preview, we weren't asked to do this, but notice at this point, I now have a pair across from each other. So if I were trying to find angle B or angle C, how would I do that? I would use the law of sines next. I could use the law of cosines because I would know all three sides, but it's simpler to use the law of sines.
Wait, if we just do a long time, can we just do that as an example?
Yes, and actually I'll make this comment. If there's an obtuse angle in this case, where would it be?
It would be,
On B.
It'd be angle B. So guess what? If I'm doing the next angle with the law of sines,
You're going to do C.
I'm going to find C because that avoids that ambiguous case. Alright, so I would find, let me switch colors here. I would find angle C by doing sine of angle C over 15 equals the sine of 10 over what I just found, 6.75. And now I know angle C has to be acute, so there's no ambiguity here. Okay, and then I can just subtract from 180 to find angle B at the end. And if it ends up obtuse, great. If it ends up acute, that's fine too, but I know that it's going to be right. Okay?
You can't say like, if B is acute or not.
We can't tell right now. Now it looks obtuse, but just from what we have at this point, we can't tell.
You can't judge by the
So that's why we're going to leave it to last. We'll get it by subtraction and we'll know for sure that we got the right one.
Okay.
Okay? Okay, so if we solve this, we get C equals 22.7 degrees. And now, it's a good thing we did find angle C first, because if we subtract those from 180, we get 147.3. Whereas if we had used law of sines to find angle B, okay, it would have given us a 33.7 degree angle. Okay, it would have given us the first quadrant angle instead of the second quadrant angle. So it's a good thing we found angle C first and just subtracted to get angle B. Okay, so get into that habit of finding the biggest angle. If you're doing the law of sines, find the biggest angle last. However, looking at our next example here, notice I have side, side, side. I can find any of the angles I want. Okay? I could find angle A, or angle B, or angle C. I'm going to choose to find angle C first, because that removes the only possible obtuse angle. Okay? If there's an angle that's obtuse, I can find it using law of cosines. Because remember, cosine is different in the first and second quadrant. It's positive in the first, negative in the second. So there is no ambiguous case with the law of cosines. All right?
Why does it being obtuse make it ambiguous?
Because sine is positive in the first and second quadrants. So we don't know which one we've got.
If it's in the first or second quadrant.
Yeah, we don't know which one it is. We don't know if angle C is obtuse or acute right now. So we would want to avoid trying to find angle C with the law of sines. Okay? That's why, since it's not an issue using cosine, let's go ahead and do that one and get it out of the way right now. Okay?
So it's okay to use the law of cosine, but not the law of sine.
Yes. If you're finding the biggest angle, you want to find it either with the law of cosines or by subtracting from 180. Okay?
Mr. Hickson, what's the problem again in using the law of sine to find the obtuse angle? Why doesn't it work?
Because sine is positive
Oh, I see.
in both quadrants, so you don't know which one is the right answer. Or maybe both of them are possible. So let's set this one up here. I want to find angle C first. So I'm going to put in cosine of C. Now, what has to go over here by itself? 64, 8 squared, okay? I put the 8 there because it's across from angle C. So now I'm going to use the other two sides, the 3 and the 6, to fill in the other parts of my formula. 2 times 3 times 6 times cosine of C. Okay? Again, I would recommend doing what you can in your head to avoid issues with your calculator. All of you can square 3 and 6, and you can multiply 2 times 3 times 6 in your head. Okay? So do that kind of stuff without your calculator. Okay? And go ahead and solve it from there. Take a minute here and solve it yourself. Alright, so some of you are getting a domain error when you tried to take the inverse cosine of like 50 something or whatever. Okay?
Yeah.
Here's the thing, guys. When we have this, and we're trying to solve this, this goes back to last unit. You have 64 equals 45 minus 36 cosine of C. You cannot subtract the 45 minus 36. That's right, it's 36 times the cosine of C.
If it was 45
All right.
minus 36x.
It's just like a 45 minus 36x. You can't combine them because they're not like terms. So you've got to get the cosine by itself. We're going to subtract the 45, so we get 19 equals a negative 36 cosine C. And then we're going to divide by the negative 36. So cosine of C is a negative 1936. Okay? That right there is one of the most common mistakes students will make with the law of cosines. Okay? The nice thing is you typically end up getting an error. So it should like, alright, I did something wrong here. Okay? The other thing that's not as obvious, the other common mistake is when people do this, they lose this negative right here. I think that's what, Hannah, I think that's what you had done, right?
Yeah, I just forgot about the
You lost this negative, so make sure you bring down the negative. And you actually end up getting the reference angle instead of the actual angle. So, but that was good, you caught that. So now we do the inverse cosine. And C is the inverse cosine
You're in reading.
of a negative 1936. And we got 121 point what?
585.
0.85, okay. So let's round, we're gonna round our angles to 1 decimal place, okay? That'll be sufficient here. So 121.9 degrees,
Oh my goodness.
okay? Now, as we go on, if we were gonna go on and solve the rest of this triangle, 121.9 degrees, I can use the law of sines without having to worry about the ambiguous case, because I already found the obtuse angle. If it were not obtuse, I know that I've just got an acute triangle, because I know it's the biggest angle possible. Okay? So now I can proceed without having to worry about ambiguous case, and we solve our triangle.
The maximum obtuse angles, the triangle can have is one.
Yes. Yeah, because triangle adds up to 180, so if you have something bigger than 90, you can't add another thing bigger than 90 to it. So, okay?
Can I go for the last one?
Yeah. Okay? So, that is it for the law of cosines. That's all I wanted to look at the law of cosines here. So, last thing here I wanted to look at, since we're on the idea of side, 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 we actually, without having to find any more information about the triangle, we could find the area of a triangle if we know all three sides. And we use something called Heron's formula. You may have run into this one in geometry class in the past, or maybe algebra 2. Okay? But Heron's formula, sometimes you'll see it written as Hero's formula. But the area is the square root of s times s minus a times s minus b times s minus c, where s is what's called the semi-perimeter. All right, you guys know the perimeter is the distance around. Peri means around, meter is from the word meaning to measure. You're measuring around something. Semi is a prefix that means half. Okay, so it's half of the perimeter. Okay? So you'll notice here I have the semi-perimeter is the perimeter, add up all the sides, divided by 2. Okay? So if I want the area of this triangle, first of all I would find the semi-perimeter, that's 3 plus 8 plus 6 over 2. So I have 17 over 2, which is 8.5. Good. And then if I'm finding my area, the square root of, and little tip for you, don't just try to type all of that in, use your head a bit. Okay, you can subtract in your head, and it'll save you a lot of headaches with parentheses when you're working on your calculator. So I know it's the semi-perimeter, 8.5, times, notice it's s minus a, s minus b, s minus c. It's just the semi-perimeter minus each side. Okay? So 8.5 minus 8 is 1/2. 8.5 minus 6 is 2.5. 8.5 minus 3 is 5.5. Okay? So I multiply those all together, take the square root, and what do we get for our area?
Square root of 58.4375.
I got the square root of 10.
Which is 7.64.
Oh, wait, I left-
7.64?
I left one out.
Oh.
Hold on.
Okay.
I got 2
It's gonna be 7.64.
Okay.
Yeah.
Make sure you don't leave out the original s times s minus a times s minus b times s minus c.
7.64.
Good. 7.64 square units. We don't know what the units are in this case, so we'll just say square units. Okay?
If I didn't have the u, is the u squared divided?
I wouldn't take off in that case if you didn't leave that, but with area it would be helpful to differentiate between lengths of sides. So
The semi-perimeter will never be less than any of the lengths of sides.
that's correct, okay? And that goes back to the triangle inequality theorem, because the two smaller sides always have to add up to more than the third. The semi-perimeter, you're right, will never be smaller than any of the three sides individually. Okay? Otherwise we'd have the square root of a negative number in there. Okay? Real good observation. Now, this is actually very, very practical, and this is something that you can use. I've actually used this a few times as I've worked on stuff at my house or just out, doing stuff. If I need to find the square footage of something that's an irregular shape, Alright, measuring angles to use side angle side isn't always, practical. But let's say I had something that was shaped like this.
You could do
Okay.
like 2 times.
Yeah, I could measure the sides of those and then measure across the middle. And then I could use herons to find that area and herons to find that area and just add them together. Okay? In fact, if I were like a surveyor trying to figure out the size of a plot of land or something like that, so I could assess how much it's worth, I could just measure all the way around the outside, measure across one of the diagonals, and then use this formula a couple times to figure out the total area. Now I know how many acres the land is, and I can figure out how much it's worth, what the taxes are, all that kind of stuff. Right? That's what a county surveyor would. That's part of what they would do.
Oh, Mr. Rickson, so then wouldn't the area be the semi-area?
No.
Just like the semi-perimeter, because the semi-perimeter is only the perimeter of one of the.
Well, it's only half of the perimeter. It still works out to give us the full area. It's just part of the derivation of this formula, which I'm not going to go into, but it actually has to do with the fact that you can inscribe any triangle in a circle. Okay? If we have a circle, any triangle can be inscribed in a circle. Okay? That's partly why this works. And actually that's why this guy Heron, he developed another formula that doesn't work for every quadrilateral, but if a quadrilateral can be inscribed in a circle, then the formula looks just like this, except it has an S minus D on the tacked onto the end for the fourth side. Okay? But again, that only works if the quadrilateral can be inscribed in the circle.
Oh, with its.
With all four corners on the circle, yeah. So,
I don't